Hello everyone, my name is Samuel Eswongan. Welcome back to my YouTube channel. This is the next video in our DevOps playlist, and today we'll be looking at containers. So we are going to see what a container is, then we are going to look at why containers became necessary, and then we are also going to look at why the industry had to transition from virtual machines to containers. Please, before we get right into it, if you are yet to subscribe to my YouTube channel, please, I would love you to subscribe to my YouTube channel, share this video, and also like and comment on this video. Let's get straight to it. So this video is intentionally foundational, and if you truly understand what we will cover here, then tools like Docker, ECS, Kubernetes, EKS, even your CI pipelines with containers and container security will stop feeling like magic and start making real sense. So for today's video, we are not going to look at commands just yet. We are going to fix our mental model first. So before we define what a container is, let me be very honest with you. Most people learn containers backwards. What I mean is, they start from the run commands, build commands, push commands, but they never understand why containers had to exist in the very first place. But in real DevOps works, in real production work, and even in some interviews, you are tested more on your reasoning than on your syntax. So in this video, we are going to walk through the evolution of software deliveries properly so that we'll get to understand why containers became very necessary. Before containers, let us look at how applications were deployed traditionally. Now let us go back in time a little. Imagine you have a very simple web application, all right? So what do? You will buy a physical server, then on your server, you will install an operating system, you will install a web server, then of course, you will install your runtime. Then before running your application. What happens with this model? This is very straightforward. And this was the original model. That is one application, one server. But then let us look at the problems with this model. Now, the very first problem, you will agree with me, is poor resource usage. Now, we all know that physical servers can be very expensive, all right? But then, most applications do not fully use CPU or memory. So at the end of the day, you will end up with one server, one application, and maybe CPU usage can be, let's say, 10%, 10% CPU, and memory usage can be 15%. What happens to the rest of the resources? They are wasted. How about the second problem? The second problem has always been dependency conflict. Now, let us imagine you have two applications, all right? Now, one application needs a specific version of Python and also a specific system library. Now, Another version or another application may simply need a very different thing entirely. All right? Putting both on the same machine quickly becomes very painful. And this is what people usually call dependency hell. How about the third problem? The third problem has always been environment differences. This is a very common problem. Environment differences. So you build on your laptop, it works very well. Now you move the same application to a server, it breaks. The reason could be operating system versions, package versions, all right? Package versions, OS versions. The fault can also be your system libraries. System libraries. Even runtime versions can also make your application break. Then this leads us to the very famous line, it works on my machine. So this problem existed long before containers. Now let us look at the very fourth problem. The very fourth problem is provisioning speed. Now, let us assume your application needs scaling. Getting a physical server can be very slow because you will need to provision the hardware, install the operating system, configure the network, and install dependencies before you can now deploy the application. This does not work very well. In fact, this does not scale well in a modern environment where infrastructure must be elastic. Now, because of these problems, the industry needed a better way to use hardware and isolate resources, or isolate applications rather. This is where virtual machines came in. So virtual machines solved the problem we had with physical servers. So instead of running one application directly on the physical server, we started running multiple virtual machines on one physical server. Now let us also look at the problems virtual machines solved. Virtual machines solved several important problems like isolation. Now each application now lives in its own operating system. Another important problem virtual machines solved is hardware utilization. Now, with virtual machines, you can run many virtual machines on one physical server, and it also solved the dependency separation. So each virtual machine can have its own runtime and its own system libraries. But then, virtual machines also introduced new problems. And this is very important because containers did not, before we get to containers, understand that containers did not replace physical servers directly. Containers did not replace physical servers directly. Containers emerged because virtual machines still had limitations. Because on a virtual machine, you will still need an operating system. Now, let us assume you have 10 virtual machines. Automatically, you have 10 operating systems. And each one of these virtual machines still needs patching, all right? Still needs updates, disk space, memory, boot time. And this makes virtual machine very heavy. So the problems with virtual machine also included slow startup, very slow startup. A virtual machine boots just like a real server. It takes time. But modern systems need to scale quickly, sometimes in seconds. Now, virtual machine images are still very large. In fact, they are in several gigabytes. So moving these images through environments and pipelines can be very slow. We also see configuration drift in virtual machines. Even with virtual machines, you often build servers like one, installing package, just like a physical server. You also configure services, just like a physical server. You also tweak settings manually or with script, just like a physical server. So over time, two servers that were supposed to be identical become slightly different, and this is what we call configuration drift. So now, the IT industry asked a very important question. Do we really need a full operating system for every application? And this is where container came in. All right? This is where container came in. So what is a container? Now, I want to be very precise here. A container is not a virtual machine, or it is not a mini or small virtual machine. A container is not a virtual machine. So you can look at container as an isolated process running on a host operating system, not a guest OS, not a virtual computer. A container is a process. So the isolation in containers is provided by features in the operating system kernel. And the two most important ones are namespaces and C groups. So namespaces allow the kernel to isolate different aspects of a process. For example, process IDs, network interfaces, host names, even users, then file system mount points. So when a process runs inside a container, it sees its own process list, its own network stack, its own file system view. But in reality, it is running on the same kernel as the host. How about C groups? So C group control how much CPU, memory, disk IO a process or a group of processes can use. Now this happens, so the combination of these two guys, namespaces and C groups, helps in the sense that containers should not staff other containers on the same machine. So technically speaking, When you start a container, you are starting a normal process, but that process is isolated, that process is restricted and limited by the kernel. Now let us answer why containers are necessary. So the next question we have is, why is container necessary? The industry moved to containers because containers helps with consistency across environments. When you package an application as a container image, you package the application itself, all right? You also package the runtime, you package the libraries, then you also package its file system. So with this, the same image can run on your laptop. The same image can run across different environments, in staging, in production, even in your continuous integration pipeline. So it is not similar, but the same. All right. This direct attacks the 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 normal phrase of "it works on my machine." So containers directly attack this "work on my machine" problem. Now, aside consistency, containers can be very fast to start up. A container starts in milliseconds or even in few seconds because you are not booting an operating system. You are simply starting a process. Then, a container is also lightweight and efficient. Because there is no duplicated kernel. There is no full operating system per application. This allows you to run many workloads on the same infrastructure. Container is designed for automation. This is possible because containers can be created and destroyed very easily. So they fit naturally into our DevOps jobs. So they fit into continuous integration, they fit into continuous deployment, and they also fit into continuous scaling. And this aligns perfectly with modern DevOps practices. With containers, microservices became very practical because microservices needs fast startup. Microservices needs lightweight isolation, and microservices also needs independent packaging. So containers makes all of this realistic. All right. So it is realistic to run many services without heavy infrastructures problem. So this is a virtual machine. On my left hand side is a virtual machine, and on my right hand side we have a container. So virtual machines virtualizes the hardware, while containers virtualizes the operating system. So because of this architecture, it is lighter, it is faster, and it is not a virtual computer. But the common misunderstanding is that a container is not automatically safer than a virtual machine. All right? If the host kernel is compromised, all containers on that host are affected. This is why in most serious production environments, you will commonly see this architecture. a physical server, then a virtual machine, then your container. And this is very common in cloud virtual machines running container workloads. So with containers, software delivery unit becomes an image. So your artifact is no longer a zip file or a binary. So your artifact is now a container image. So this completely changes our CI and CD pipelines. So let us look at a very brief summary. So in physical servers, what do we have? We have one operating system per machine. We also saw that it is very slow to provision and low resource efficiency. Then how about virtual machines? A virtual machine has one operating system per virtual machine, just like what we saw here. One operating system per virtual machine. Because of this architecture, it also has a very strong isolation. But then, just like a physical server, it is heavier and slower to start. But in containers do not have a guest operating system. But instead, they have a shared kernel, and it is very fast to start up, and because of this architecture, it becomes lightweight and very portable. So to end this video, understand that virtual machines virtualize hardware, containers virtualize the operating system. So this simple explanation will help you avoid many common mistakes. So understand that this video is only the foundation, and in the next video, we are going to see the practical layers. So we are going to look at container images. We are also going to look at how images are built. Then we'll see base images, build context, and common mistakes that create huge images and slow pipelines. Thank you for watching, guys. I'll see you in the next video where we start working with containers properly. Please, as usual, do well to like this video, comment on this video, share this video with your friends, and also subscribe to my YouTube channel. I'll see you in the next one.